Okay, write the electron configurations of hydrogen through sodium. So I'm going, as I said before, I'm going to assume that you've looked at the book, you have some idea of what I'm talking about rather than doing the full-out theory. That's what I do in lecture. But we have a mnemonic that we can use, and this is in your book. And then we're also going to do it by the periodic table, which I have on the back here. But these, you can see that the we have 1s, and then 2s, 3s, 4s, 5. So you can make this up in the exam if you need to, but you can also use the periodic table to fill up these electron configurations. And then you see next here we have the p orbitals, d and f. And that if you follow this arrow through, you will fill up the proper orbitals as we go, or the proper energy levels and sublevels. So let's take a look here. So how we do this is hydrogen has 1 electron, so that is 1s1. So we use this, and we just start here 1s1, and we have a superscript for the number of electrons. And remember that s can have 2, p can have 6, d can have 10 electrons, and the f subshell can have 14 electrons. Shouldn't really be equal signs, but you know that's how many you can have in each. So 1s1. We go to helium, which has 2 electrons. That is 1s2. Lithium has 3 electrons. Now we have 1s2. And the s subshell can have only 2 electrons. So we have to go to the next one, 2s1, which we follow along here. 1s2, 2s1, and we keep filling up. So we have beryllium is 4 electrons, 1s2, 2s2. Boron is 5 electrons, 1s2, 2s2. We filled both of those up. We filled up the first energy level. We filled up this subshell for the second energy level, so we get a 2p1. So 1s2, 2s2, and then we go to here, 2p1. Now the p orbitals can have 6 electrons, so we just keep adding them. Sure, yeah. So this is 1s2, 2s2, 2p2. Nitrogen has 7 electrons. 1s2, 2s2, 2p3. Oxygen has 8 electrons. 1s2, 2s2, 2p4. And if you get the full idea of this, that's fine. Just follow along or fast forward, whatever you have to do. 2p5. And then we have neon. 1s2, 2s2, 2p6. Now notice we filled up the first energy level, and that's helium. When we filled up the first and second energy level, that's neon. Those are noble gases. So when we fill up an entire energy level, that's when it's the most stable. That's when it's the happiest, and that's why the noble gases don't really react, because they have a full subshells, they have full shells, they're absolutely happy. So subshells and sublevels, shells and energy levels, those are the same thing. So energy level and shell, or energy shell, are the same thing. And then sublevel or subshell mean the same kind of thing. Okay, so, and then the reason I go to sodium is 1s2, 2s2, 2p6, 3s, and then that's 10. Sodium has 11 electrons, so 3s1. We go to the next level, and on we go. And we can make up electron configurations for every element that we have in the periodic table. Okay, now, so write an electron configuration of fluorine that goes against the Pauli Exclusion Principle. Okay, so fluorine has, well, we just did it, had 9 electrons, so it should be 1s2, 2s2, 2p6, 2p5. This is correct. So we could do something like 1s3, 2s3, 2p3. This is fine, but this goes against the Pauli Exclusion Principle. We can't go any further than, it says no 2 electrons in an atom can have the same 4 numbers. So if we look at the quantum numbers of, in this case, for 1s, this is n is equal to 1, l is equal to 0, m sub l is 0, and then m sub s can be plus 1/2 or minus 1/2. If we have 3 electrons in this orbital, then we have the 2 sets that we can have, and then the third one would have to double. They all have 1, 0, 0 to be in this subshell. In this case, it's just an orbital. One of the electrons would be plus 1/2, the other would have minus 1/2, and then the third would have to be one or the other, which would mean that it's copying one of the other electrons. So what we can't have are 3 electrons in the same s level. We can't have 7 electrons in a p sublevel. Once we hit 6 for p or 2 for s, we have to move on. So this would be an incorrect one, which is what they were asking for. Now write the electron configuration for technetium using the mnemonic diagram and then the periodic table. So the mnemonic diagram, first what you want to do is find out how many. We have 43 electrons for technetium. And I'm just going to do it by the mnemonic, assuming that you have one sitting next to you. So it's 1s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now that means we have 2, 4, that's 10, 20, 30 electrons so far. Then this would make it 36, 38, and then 4d5, that's 43. So that is our electron configuration. Now, that's nice of you to use the mnemonic because it's pretty easy to draw, but if you look at the periodic table, it's set up so that we can pull the electron configuration directly off of it. If you notice this column, this would be considered the S group. Then these are the D's, and then these are the P's, and then down below this would be the F group. If we wanted to look at hydrogen, we know that it's 1s1. Well, hydrogen is here, 1s, and then there's 1 electron, so 1s1. And then we have, let's say, lithium is 1s2, and then 2s. Notice there's no p orbitals over here, so lithium would be 1s2, 2s1. So if we just follow the blocks, we can fill them in as we go. For technetium, since I have this already written out, I don't know if I can do the whole. Well, you can just try to remember that. There, we got it. Maybe I can put it right at the top there. Okay. So for technetium, we're down here. So we just fill in. We have 1s2, 2s2. Then we look at this side over here, 2p6. 3s2. So if we were to do each of these elements out, we would fill them up as we go, 1 more electron down the line. So this would be 2s1, and then 2s2, and this would be 2p1, 2p2, 2p3, 2p4. And you'd see that for oxygen, it would end up with as 2p4. That would be its last term. So if we follow this along, we can say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then this is 3d, 3d10, 4p6, 5s2, 4d, 1, 2, 3, 4, 5. So 4d5, that would be our last term for technetium. So following the blocks as S blocks, P blocks, D blocks, and F blocks, and then following these numbers on the side, the period or row number, we can get the same electron configuration. Now, if you're seeing me doing that, just like, what was that? Then use the mnemonic. But what you want to do is, you know that the molybdenum, let's say, let's just go with technetium. Let's just do it with the last term. We see that it's in the D block. This is the 3D, and then the 4D level, and then it's 1, 2, 3, 4, 5. So we know the last term for technetium is going to be 4D5. And it is. if we as we know what the last term will be just looking at where it is in which block and which period or which row. But we can also follow through the periodic table and just get the same electron configuration as we go, just going from block to block, section to section, filling up as we go. So if that doesn't make a lot of sense, you have the mnemonic. The mnemonic will work just fine. But the periodic table contains all that information as well. Okay, so get that. Bismuth. If we use the mnemonic, it's going to make sure I get everything right here. It's going to be, for bismuth, it's going to be 1s2, 2s2, 2p6, 3s2. Notice it's always the same order, and we just keep putting more and more electrons in. And then if you run out of room, then you have to go to the next line. That's fine. Now when we get to 6s, we go to 4f. Now we're into the F subshell. And so this is a big guy. Now, looking at the periodic table, I could have guessed what the last term should be for bismuth. Because it's 6p, it should be 6p3, and it certainly is. Using the periodic table, I'd say 1s2, 2s2. Let me back this off a little bit. Oops. Make sure I have everything on here. Yeah, why not? Let's do that. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then we have to drop down here 4f14, and then 3, 4, 5d10, and then 6p3. And that's where we'd end. And if you read that back, you should come up with the same electron configuration that I have here. Okay, let's go back in here. Now what is the noble gas core for boron and for sulfur? Well, let's write out, let me get the periodic table here. So for boron, it's 1s2, 2s2, 2p1. The noble gas core is any filled energy level, and it's 1s2. Now if you look, 1s2 is also the electron configuration for helium. So the noble gas core is 1s2, which is the electron configuration for helium. And we normally put helium in square brackets to indicate that. So these are equal. For sulfur, it's 1s2, 2s2, 2p6, 3s2, 3p6. Oh, not 3p6, it'd be 3p4. That's electron configuration for sulfur. So we look back at what has been completely filled in by energy level. 1s2, 2s2, 2p6, that is neon. So 1s2, 2s2, 2p6 is neon, so the noble gas core for sulfur is neon. That is a complete set of energy levels. Now when we haven't filled up our N is equal to 3 levels yet, so that's not a noble gas, we haven't reached the noble gas configuration, which is a very stable one. So the noble gas core, first it shows us that we hit these points in the electron configuration that are very stable, and then when we go beyond that, we get to the more reactive elements, and sulfur is definitely reactive. But then we're also going to be able to use this down the line. All right, let's take a look here. Write the electron configuration for silver and for rubidium using the noble gas core. So we're going to see that silver is here. The noble gas core is the noble gas that we come to first as we go back down the line, and that's krypton here. And krypton is, well, let me write it out here, the full thing for silver. So for silver it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I should also say in your book, our book, they group all of the n is equal to the n levels together. But the 4s2 comes before 3d10 as far as energy. But once you want to follow this along first, but if you want to then regroup them, all the 3's together and all the 4's together, that's fine. But first make sure that you fill them up correctly. So I won't hold that against you on an exam. Definitely. So 4p6, and then we have 5s2, 4d9. I think that's it. 10, 20, 30, 30, and then 40, 47. Yep, everything's there. And then the krypton is 30. It goes. See, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then here, if we just took this electron configuration, that's krypton. So instead of writing everything out, for silver, we could just write it as in that form. So that's the shortcut. Now on the exam, I'll ask you to write out the full electron configuration, then I'll also ask you to write it out in the shorthand form. So I just want to make sure you can do both. But rubidium, notice where rubidium is, it's 1 after krypton, so rubidium is just this. You can see how simple it can be if you use those shortcuts. And so, well, why don't we use them all the time? Because at first I want to make sure that you can write out the full electron configuration, and then go ahead and use the shortcut for the rest of your life, if you so choose. Germanium, the pseudo-noble gas core is the noble gas core like we talked about, but then the completely filled D level, if it has one. So germanium has argon as its noble gas core, and then it also has a full 3D level. So we include that because once the D level is full, that's also a very stable point too. And then, but not every element has D electrons, and not every one of them has a full D shell, but it has to be full, or subshell I should say, needs to be full. So indium is has krypton, and then it has our so it has 4d10. This is not the electron configuration. It's just the pseudo-noble gas core. So you say, well, that's not the electron configuration of germanium. Absolutely, it's not. It's the pseudo-noble gas core. Just like this is the noble gas core. You wouldn't say that that's the electron configuration of germanium either. It's the noble gas core, which is another type of question that could be asked. Okay, the last two things here. Chromium, I'm going to do this quickly because we're running out of time. This is what chromium appears to be, but this is incorrect, and that will be part of the exam, is to see if you are paying attention to these differences. This is an exception, and we have to note exceptions because exceptions are what is actually happening, or what actually is happening in nature. We can't deny it. We try to come up with these simple rules, but when there are exceptions, we can't just say, oh no, well, that's just a little nothing. It's important. What happens here is that one of the electrons shifts over to half fill I should say this is D. Oh, poop. Yeah, let's get this right. It's all right except for one thing. 3s2, 4s. This is 3d4, and again, this is incorrect. Those both above were incorrect. But the D subshell can hold 10 electrons. 5 means that it has a half-filled subshell, and that's very stable. So what happens in reality is we get this. And this is the correct form for chromium. For copper, we are right up against it now. This is what it appears to be. This is what it actually is, where one of the electrons goes over to the d orbital.